Welcome to this first colloquium of the year. We will dedicate today to the Nobel laureates that were awarded this last Sunday. And we will focus on chemistry and physics, which are at the heart of our research in this institute. And for that, we will have three researchers of our institute. They will present the fields that have been awarded by the Nobel Prize. First, we will have Beatriz Juárez. She's chemist and a physics tenor researcher working on the synthesis and characterization of nanoparticles for applications ranging from nanomedicine to optics. Bea, Dr. Juárez, has been working at the University of Hamburg, where she worked with a world leader in quantum dots, Horst Welle. And then in INDEA Nanociencia and UAM, Universitat Autónoma de Madrid, where she has been Marie Curie and Ramón y Cajal Fellow. She got the Nanotechnology Prize in its junior version, awarded by the Association of Nanotechnology Competence Centers of Germany. And she has supervised 5 PhD theses related to the studies of nanoparticles manufactured with the Nobel Prize winning method. Then we will have Rui Ferreira da Silva. He is theoretical physicist and La Caixa Junior Leader Fellow in this institute. He is specialized in the behavior of matter under optical excitation in the strong field regime, and he has been working at the UAM, also in the group of Fernando Martín, studying the atomic molecules under intense laser pulses. He specialized in quantum dynamic simulations of systems subjected to strong electric field excitations. Also at the Max Born Institute in Berlin, in the group of Professor Mikhail Ivanov, studying high harmonic generation in solid-state targets, and back at UAM, in the group of Johannes Feist, where he studied ultrafast molecular polaritonics. And finally, we will have Álvaro Jiménez Galán. He is also a physicist, and he is a Talento CAM fellow here working in the institute on the interaction between light and matter at the attosecond time scale. Dr. Jiménez has worked at UAM, at the Universidad Autónoma de Madrid, in the group of Professor Fernando Martín and Luca Argenti, developing tools to study correlated electron dynamics in gas atoms with attosecond interferometric techniques. He obtained the best PhD thesis of the Comunidad de Madrid in the field of chemistry in 2015. He worked also in the Max Born Institute in the group of Professor Misha Ivanov, studying highly nonlinear optical response of matter under strong polarization tailored light fields. And finally, he worked also at the National Research Council of Canada in the group of Paul Corkum with a Marie Curie Fellowship to perform high harmonic generation experiments in 2D materials. So the three of them will give us short presentations describing the Nobel Prizes in chemistry and physics, and we will start with Bea. Thank you.
Okay, welcome everyone. Thank you very much. First, I would like to thank my colleagues in the seminar committee for suggesting me to give this talk and to be here today with you. So, talking about the Nobel Prize in Chemistry of this year, 2023, this Nobel Prize this year has been awarded to Moungi Bawendi, Brus and Alexei I for the discovery and synthesis of quantum dots. I have to say that while Alexei I and Brus have been awarded for the discovery of the material and understanding of their optical and electronic properties in the context of the quantum confined effect, Moungi Bawendi has been awarded by the developing of a synthetic chemistry approach that allows nowadays to produce nanocrystals with very high quality. Alexei Ekimov made all his achievements basically in the former Soviet Union in the 80s of the last century, but has been living in the US in the last decades. On the other hand, Brus has been emeritus professor at the University of Columbia, and Moungi Bawendi has been working in the last decades in the MIT. So let me start with this slide, which is courtesy of Professor Alexander Eichmüller for the University of Dresden. He presented this slide in the defense of his habilitation already in 1999. So he presented this nano genealogy, he called it, this family tree, summarizing people that was working on this topic already from the 80s. So here in the first row, you find people like Hangleim, sorry, is here. Hangleim, Ekimov, Onushenko, Efros, or Brus. And in the second row, you already find Bawendi. So in the first and second rows, you already find the three people awarded with the Nobel Prize this year. But maybe you also recognize some very other personalities very important for the development of this topic in this field. Like, for example, Efros, who has been working in the theoretical to develop theoretical approaches to understand the optical properties of nanosemiconductors, as well as Beatriz H, who has tremendously contributed to the field in the last 40 years, as well as Vela, with whom, as David said, I had the privilege to work with for 3 years. So, some other personalities you may be here familiar with, for example, Gretzel, that also worked in the group of Hangleim, made the PhD with him. Sorry, this pointer. Okay, so this Nobel Prize was already predicted long ago, because if you search in the Thomson Reuters platforms, for example, you can see how in 2012 already Louis Brus was candidate to get this Nobel Prize. In 2013, Paul Alivisatos was also a candidate to get this prize, as well as Moungi Bawendi on the 2020. So let's start with a very basic definition of what quantum dots are. Quantum dots are semiconductor materials structured on the nanometer scale, which have, from a basic point of view, approximately 100 to several thousand atoms and exhibit varying properties depending on their size, mainly electronic and optical ones. So what I will explain to you now, just to contextualize the scale, is a video performed out of a superposition of different transition electron microscopy images, in which you will see the crystals that can be performed nowadays by the method awarded with the Nobel Prize from Bawendi. So this is a video that it's a courtesy of Professor Horst Vela and Andreas Konowski from the University of Hamburg. So here nowadays, these crystals that can be performed, as I said at the beginning, with high quality, I need to find here. I cannot see the pointer. Yeah, here it is. So here what you see, it's a cloud of material that at some point it's getting more and more clear. So these are the nanoparticles produced by the Bawendi method out of transmission electron microscopy, where we just drop a colloidal solution on top of a TM grid and see how these entities start to get closer and closer, exhibiting the crystallinity, as you can see here. And nowadays, with this ultra high resolution transmission electron microscopy, we can reach even sub-angstrom resolution, as you can see here. So this is really impressive nowadays, how technology gives us the tools to be able to observe materials at the nanoscale. So I said that these particles show varying electronic and optical properties. And of course, this is something that was well known years before. So for example, in the last century, in 1937, Froelich theorized that small particles, in this case metallic, should behave differently than the bulk material, that should have variable properties as a function of size. We can even think or argue that Faraday did it already in the 19th century. But it was not until the 80s, in the last century, that this effect was indeed experimentally verified. And this is what Ekimov and his collaborators did. So Ekimov was working on doped glasses, in color glasses, which are materials, are vitreous matrices that can be doped by the inclusion of several substances to make them colored. So what he observed upon mixing several components in his glasses is that the absorption spectrum, as you can see here marked with number 2, the absorption spectrum of a non-doped glass was completely different to the absorption spectrum of the glass doped with a compound containing copper and chloride. So he immediately realized that inside of this glass he had cuprous chloride, or copper chloride 1, which is exactly the absorption spectrum that you can find here for the bulk material. 1 year later, he published another paper in which he saw that these absorption peaks in the absorption spectra moved, blue shifted, with the different treatments that he performed with his glasses. So he performed different treatments, heating and annealing processes, and then he observed how these peaks moved and blue shifted. And then he evidenced that this shift is related to the size of the particles that were embedded in the crystal, in the glass. And this was made by a small angle X-ray scattering, and in this way, I say they evidence the presence of these small colloids in the glasses. So, but furthermore, he really contextualized this as in the frame of the quantum confinement effect, where electrons or holes can be confined in the small size of the crystal. And due to this confinement, due to this especially confinement, these particles sometimes are called artificial atoms. You may have heard of that. So you may have heard that the quantum dots are called artificial atoms. The reason is just that they show discrete energy levels. So for example, in this slide, very easy, like the idea is if you compare the HOMO-LUMO level of a molecule and compare it with a bulk semiconductor that contains a valence band, a conduction band, you see how the nanoparticle should behave, so it should be marked in an intermediate state, where as you can see here, the difference in the energy levels increases, as well as the energy gap, as soon as we make the particle smaller, the quantum confinement effect. So the question is, how many atoms do we consider to be at the nanoscale, for example, for these nanoparticles? So for you to have an idea, a 1.5 nanometers in diameter of cadmium selenide nanoparticle contains around 50 atoms, while a 10 nanometer in diameter cadmium selenide nanoparticle has around 10,000 atoms. So when this tunability of the energy gap lies in the visible range, this is the reason, so these discrete energy levels make us sometimes to understand these crystals better from a molecular chemistry point of view when the crystals are very small, or from a solid state physics approach when they are a little bit bigger. So as I said, when this tunability in the optical gap lies in the visible range, our eyes are able to see the different colors that also Ekimov observed in his glasses. So in this way, as an example, for cadmium selenide nanoparticles, if we have particles of around 2 nanometers, let's say, we can have a band gap Li in the blue. As soon as we increase the size, of course, we will get behaviors closer to the bulk material. And in this way, when we have these particles dispersed in a liquid, so we have a colloid, then what we observe with our own eyes is the change in the color depending on the nanocrystal average size in these solutions, ranging from 2 nanometers, here the vial on the left, to 5 nanometers, here the vial on the right. Of course, if you take the absorption spectra, you of course observe the shift in the absorption edge. As these particles also show photoluminescent, under the excitation of UV light excitation, you observe this very nice photoluminescent response, giving you very narrow size, very sharp colors and very defined colors in the photoluminescent response. Okay, so these colloidal solutions were the ones in which Brus was working already in the 70s, of the last century. So he was studying photochemical reactions on cadmium sulfide nanocrystals by Raman spectroscopy. So apart from the Raman response, he also observed here, as you can see here better in this inset, so the absorption spectra of 2 colloidal solutions. One which was aged, so that the spectrum was acquired 1 day later after he prepared it, and another one who was fresh. And by transmission electron microscopy, he could understand that this difference in the absorption edge was related to the mean size of the particles that were in the colloid solution. In this paper, he didn't indeed include these TM images, but he did it also for in another systems years later. Another of the legacies of Brus in this case is what we call the Brus equation. It's a simple expression that gives us the tools to predict the optical properties of the particles depending on their size. So this Brus equation contains basically 3 terms, one related to the bandgap of the semiconductor, and 2 other extra terms, mainly. One related to the quantum confinement. Look how here we have the particle in a box expression with, in this case, electrons and holes, and another term, which is the Coulombic term, due to the fact that we have charges, punctual charges, that can interact. Okay, so following with this family tree, telling you that Brus was working on the US in the Bell Labs when Livisatos joined his group in 1986. And by that time, also from in Germany, Hangleim and Vela were doing a lot of efforts in studying different topics in these crystals, like, for example, luminescent annihilation processes, nonlinear optical phenomena, chemical degradation, and especially Vela improved synthesis and novel structures and applications ranging from photovoltaics to biomedicine. So in 1988, Bawendi joined the Brus group, and later on he moved to the MIT, where he worked with Norris and Bawendi. And these 3, they were the co-authors of the seminal paper that I will talk about. So just a curiosity, if you search the Bell Labs where Brus was working at that time, among many other prizes, they have already 10 Nobel Prizes passing through these labs. Not bad. Okay, so going with the achievements of Bawendi and his collaborators, so what they published is a methodology to produce nanocrystals very easily, in principle, controlling all parameters in a way that you can control the size and the polydispersity of the sample. So you can produce crystals which are very similar, let's say with very narrow size distribution out of this method. So this is the original absorption spectra that they published in 1993, where you see this absorption edge shift depending on the size of the crystals, and a TM image for that time. So this is something that you can do very easily in a small scale in the lab, as soon as you have a Schlenk line and a hood. In every inorganic or organic chemistry lab should be able to perform this kind of synthesis. So, and the key of this synthesis was to control and to separate the nucleation and the growth of the particles. So once you nucleate the first seeds, the rest of the monomers and species in solution should be only available to grow their pre-existing nuclei and not to grow further seeds. And this is just the key of the separation of nucleation and growth that gives us the option to produce very, very monodispersed samples. This was something that was based on the already procedures developed by Lamer and Dinegar already in the 1950s to produce submicrometric spheres of silicon oxide. Okay, so but how is a particle? A particle indeed is not like this. So we have seen at the TEM images that we have very nice particles with, where we can distinguish the crystallographic facets. But indeed, the particle is not like this, but it's like this. So it's covered and passivated with organic ligands that otherwise, that provides them the colloidal stability in solution. Otherwise, they will be all flocculated. So, an understanding how these ligands attach, indeed, the nanoparticle surface. So, understanding how these ligands attach to the nanoparticle surface, how they passivate the surface from different perspectives. So from analytical chemistry, from analytical tools, surface science techniques, theoretical models. It's really, really important in order to control not only the size, but also the morphology of these systems and the dimensionality. Because nowadays we can produce not only quantum dots that are zero-dimensional, as you can see here, but also one-dimensional or two-dimensionals of different systems and combination of different semiconductors, as you can see here, in such a way that we have optical responses in the UV, visible, and near-infrared and mid-infrared ranges of the electromagnetic spectrum. So, I would like to highlight a couple of milestones that have been reported during the course of these years, which I think they are very important for later on understanding the applications of these quantum dots. So one was reported also by Brus, Livisatos, and other co-authors in 1996, And it's a property, it's what it's called the blinking of the nanocrystal. So this means the intermittency in the emission of these nanocrystals. So when you have an ensemble, you cannot distinguish this blinking effect. But when you have them individually and you study them individually, then you see this blinking effect. As I said, this intermittency in the PL, in the photoluminescent response, giving rise to these on-off states. And of course, this is bad for applications because your crystal cannot be in an off state if you want them to be a source of light. So, of course, this comes from the fact that the crystal is not perfect, has a lot of surface and other defects that yields indeed surface traps and deep traps. And if I have a perfect crystal, what I have is a normal photoluminescent response in which one electron moves to the valence band, leaving a hole behind, and the luminescent and the photoluminescent, the recombination of this whole pair emits light normally. Okay, but if these deep and surface trap states, what makes or what forces our crystal is to get into different processes that kill this luminescent response. And one of the most important one is what is called the non-radiative Auger recombination, in which, not giving details, but basically it includes the formation of bi-excitons, so 2 electron hole pairs, and an energy transfer to a third carrier. And this, I only say this because this process is what it's nowadays a bottleneck to use these nanocrystals in devices instead of being optically excited, electrically excited. And I will come back to this later. In the Auger process, there is later on another extra process that thermalizes, and then it gets back the carrier. So this is just one part, but there are ionization, so there are several processes that go on. Okay, so the way to solve this problem of blinking. So so it was recognized that the way to reduce this blinking was, first of all, to passivate the nucleus of a particle with another semiconductor. And you can do it with another semiconductor which has an energy gap, either covering the band gap of the core or in a staggered energy alignment, as you can see here. So in this way, in the first case, we have electrons and holes included the wave functions in the core in such a way that the luminescent response increases enormously with respect to the core only. And in this other case, we can separate electrons and holes in the different semiconductor parts. And these kind of approaches have been used very much in photovoltaics, where you want a separation of charges and to be able to control these charges. So by doing this first type 1 method, so by covering the semiconductor with another semiconductor with a higher band gap, it was evidenced already in 1996 that this blinking was very much reduced, but it was not totally reduced. And so the problem is that sometimes when you have an abrupt interface in between the core and the shell, here the lattice mismatch of the mismatch in between the lattice parameter of the 2 semiconductors produce more defects. And then that's the reason why the crystal is not a perfect emitter. So the way to solve that, it was to produce, like radiated shells, radiated nanoparticles, in the way that you can produce nanocrystals which are not composed of abrupt shells, but graded composition from the core to the shell, and in this way the lattice mismatch is not as strong as to produce defects in these structures. Okay, so I will talk now briefly about the applications of these colloidal quantum dots. I will not talk about the applications of other quantum dots produced, for example, by molecular bin epitaxy, but just the ones that have been produced in colloidal solution. So here we find plenty of applications ranging from photovoltaic cells, solar harvesting devices, lighting, displays, cameras, lasers, detectors, in quantum technologies and nanomedicine, including diagnosis, imaging, drug delivery, and therapy. So out of all these applications, I would say that these 3 ones in photovoltaics, quantum information, and sensors, there is still a lot of room for improvement. So this corresponds to, this slide corresponds to an interview made to Bawendi on the year 2013, when Sony decided to include these quantum dots in televisions. So this was the first example of how the luminescence of quantum dots can be integrated into a technologically in technology. So this was the first TV that was available on the market, as I said, by Sony. In this kind of TVs that probably you may have at home, in the configuration of these TVs, we have a blue LED here at the back that optically excites quantum dots that emit in the green and in the red colors, in such a way that we have the red, green, blue that we need for the displays. Another configurations are being studied or being implemented to have smaller quantum dots as well emitting in the blue, and other combinations, like for example, Samsung in 2021 decided to include a combination of the Q dots emitters with no LED, organic light emitting diode, in their TV panels. The next generation of TVs, in principle, is just to get that these particles, instead of being optically excited, that they can be electrically excited. So this means to inject charges, to inject electrons and holes in such a way that the particles can emit without being photoexcited. And this is a bottleneck still in the industry, as far as I understood. And I gave you the reason why this is a bottleneck. So these mechanisms in which the PL drops because of this, because of this way to relax. So the next generation will be composed, as far as I understand, of these graded shells surrounding quantum dots. Yeah, so by exploring these systems, it's feasible that the next generation will be successful in this respect, with electrically excited quantum dots. Indeed, this year, the group of Ekimov already published a paper in which quantum dots can be electrically excited to produce an electrically excited laser. And the idea of integrating these particles in devices is very easy. So because we can place them, since they are in solution, we can place them between electrodes, as you can see here in this CM image. Yeah? So it's super easy to make them, to integrate them in field effect transistors, on photodetectors, in light-emitting diodes, or in solar cells in different planar configurations. That's the reason why I think they still have room to produce many other applications. So in terms of LED, infrared, LEDs in the infrared, solar cells, I think nowadays these cadmium chalcogenide nanocrystals that I've been talking about, that were the ones developed by Bawendi and his collaborators, nowadays the quantum dots produce, or the perovskite type quantum dots like cesium lead allied quantum dots are gaining a lot of attention because in principle they show better performances for these kind of devices, as well as for quantum computation, quantum information. So concerning photocatalysis, these quantum dots have also been used for different applications like the hydrogen or oxygen generation, or for the water purification, reduction of CO2, etc. In this case, there are plenty of literature where you can find quantum dots that combine not only the semiconductor part, but also in combination with metallic parts, as you can see here. But I will say that these applications are, in these applications, the kings are nowadays the carbon dots. Concerning the bioimaging and medicine, or in nanomedicine, there is also a lot of work done since the pioneering work in 1998 of two different groups, the groups of Alivisatos and the group of Ni. They both published two papers in Science, where they demonstrated that quantum dots can penetrate the cell membrane of a cell, and they can be low as toxic. So What you can see here are images of a nuclei, of a nucleus, stained with quantum dots emitting in green, and some actin fibers where quantum dots are emitting in red. So this was something that until that time was only only dyes or proteins were used at that time, and the use of quantum dots allow for a more intense research because they are not, they do not photobleach as dyes, for example, do. And since this starting point, since these two seminal papers, there has been a huge amount of work developing quantum dots as emitters in biology, because you can easily combine here proteins, antibodies, ligand conjugates, cationic peptides, RNA, DNA, etc. And you can also produce quantum dot sensors out of these quantum dots because you can functionalize also the surface with different ligands that can react with different analytes in solution and to detect or its present by changing their emission state, so on-off states. Another field in which they have been using is for the in vivo imaging of tumors, of solid tumors. As you can see here, also in this pioneering work, in which a tumor can be detected by quantum dots. In this case, these quantum dots were emitting in the visible range, where there is high optical scattering and absorption of tissues. So the idea nowadays is to move to the near infrared, to what is called the first and the second biological windows, where this optical scattering and absorption of tissues and blood, etc., is reduced in such a way that you may have deep tissue imaging, as you can see here in this example, where by using quantum dots that emit in the near infrared range, you really have a high resolution of and high contrast of what you can want to study in this for this topic. Another example is, for example, in this to resect a tumor with high accuracy, because as you can see here, the contrast between the tumor and the healthy tissue is very sharp, and therefore it's a very good solution to make this resection the best as possible. And I would like just to finish with this other application, which is still in its infancy, which forms part of the US Brain or the Interbrain Initiative, which is the goal is to have a real-time voltage imaging by quantum dots of the membrane voltages of neurons. So to analyze and to detect the way our brain works is not easy, but medical doctors, for example, nowadays know some ways to detect it, for example, by non-invasive or invasive approaches, including electroencephalography or patch clamp techniques. And the idea in these platforms, in these projects, is to use quantum dots to be able to detect these membrane voltages, as I said, in order to have a map to image a huge amount of neurons. The reason why you can use quantum dots for this topic is because the quantum dots can also modify their emission in the presence of electric field. It's called the Stark effect. And they can also communicate with different molecules or entities by energy or charge transfer. So with this, I will just go into the conclusions. The discovery of the relationship between the optical properties and size in these crystals has opened an enormous range of studies and possibilities. And from the point of view from the chemistry point of view, the work of Murray, Snorri, and Bawendi has facilitated the fabrication of a wide variety of materials, but not only semiconductors, because nowadays you can use this technique, this hot injection method, also to produce dielectrics, to produce magnets, magnetic particles, etc. So I wanted to show this slide in which I had the opportunity to meet all these people that has contributed enormously to the field in the last years. Here we met on October last year with Bawendi. He was still not aware of his Nobel Prize, and many other people who, as I said, really contributed to the field. And just an announce, if you want to read more details about this, but in Spanish, there will be a next issue in the Revista Española de Física that I wrote together with my colleague Luis Liz Marzán on the topic of this Nobel Prize, and some others that you can read if you want, if you're interested in Spanish. Also, you can read it in Anales de Química 2011 or this Investigación y Ciencia, which is the Spanish version of the Scientific American in 2014. And with this, I just thank you for your attention.
Okay, we will make a break here now. Do we have any question for Bea about this presentation? Yeah, right.
Just a very small one. So in living organisms, when you inject these nanoparticles, can you create illnesses or kill the subject? Yes, exactly. So you are, I mean, it's good for something, but then you are.
For this until now, they are indeed cytotoxic. It depends on the coverage. So if you are able to block the release of cadmium ions, in principle your particle is not cytotoxic. But this is not in any clinic, so it's not still in the clinic at all. Because nowadays what we are doing is searching for materials which show less cytotoxicity, and cadmium selenide is not the best example. So I think all the proof of concept has been done with this material, but now people is moving to another systems.
All right, if we don't have any question, let's thank Bea again, please. Now we will move to Rui and Álvaro presentation. They will share the presentation, to describe the Nobel Prize in Physics.
Okay. Well, thank you very much first for inviting us to give this talk here. Thank you for a nice presentation. So I'm Álvaro Jiménez. I'm the first of two speakers on this. Yeah. Like this? Okay, perfect. So as I was saying, I'm Álvaro Jiménez. I'm the first of two speakers. The next one is Rui, who will present the Nobel Prize in Physics 2023, which went to attosecond science for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. And it went 1/3, 1/3, 1/3 to Pierre Agostini, and Lullier, and Ferenc Krausz. So I hope I can give an overview of the field in the next few slides. So the smallest object, let's first focus on length. Smallest objects the naked eye can distinguish is more or less approximately the size of a human egg, which is that white dot that you see there next to the coin, if you see it. This is approximately 0.1 millimeters, and technology, as we have heard, has now allowed us to go down by 6, 7 orders of magnitude towards essentially the size of an atom with scanning tunneling microscopy and other methods. And regarding time, the fastest time that our brains can process a visual cue is approximately the same time as a blink of an eye, which is 100 milliseconds. And technology here has now allowed us to go down 17 orders of magnitude. This is a huge number. Just to give you an idea, there are as many attoseconds in 1 second as seconds are in the age of the universe. So it's really remarkable. And the first question you might ask is, why do we need such short timescales? And maybe some of you are familiar with this picture. This is the first picture ever taken of a person. And so there is the person. And the fun fact of this picture is that it was taken in a busy street of Paris in 1838. So where are the rest of the people? Well, you cannot see them because the exposure time of this picture is over 7 minutes. So anyone who is moving faster than this time scale is just washed out from the picture. So the only one remaining is this stoic man who stood there for over 7 minutes, standing still, cleaning his shoes. So of course, now we have temporal access to the macroscopic, like our cameras, phone cameras. I don't know what keeps going. So our phone cameras can take pictures in the milliseconds now, which is enough to see the motion of every macroscopic object. But what about the microscopic? So what is the time scale of the constituents of matter? And the short answer is that it depends on the separation of the energy levels, right? So, for example, the vibrational states of molecules are are separated by milli-eV, and so atoms in molecules move in the picosecond to femtosecond time scale. So accessing these time scales allows us, for example, to see the rearrangement of atoms in molecules following chemical reactions. And this is a field of chemistry called femtochemistry, which was pioneered by Ahmed Zewail, and which won the Nobel Prize Physics in 1999. And but if we go even larger in energies, shorter in time, so that the energy separations of bands in semiconductors or of electronic states in atoms are few eV, tens of eV. And so electrons in atoms move from the femtosecond to the attosecond time scale. So attosecond science is really the science of electrons in motion. Having access to these time scales allows us to monitor and control electronic dynamics. So how did we achieve this short time scale? So let's go a bit back in time. So many of you are probably familiar with the photoelectric effect. We have a photon coming in to some material, and if the frequency is higher than the work function of this material, then we have electrons coming out. So I took this picture from Wikipedia, and actually we should also have here the light that is either reflected or transmitted from this material, which has the same information as the electrons that go out. And this is the beginning of laser spectroscopy, essentially. And the invention of the laser in 1964 gave us this access to the ultra small. Now, we're all used in everyday life to a linear response, where if we have, we input some frequency to a medium, we get out the same frequency. So we have a laser pointer, a red laser pointer, we point it to the mirror, and what we see is red. We don't see blue, for example. But if the intensity is high enough, then we can see integer multiples of this fundamental frequency. We can see not only the fundamental frequency coming out, but also its second harmonic. So what happens is that 2 photons are absorbed and a big photon is emitted. And we can go higher, so maybe 3 photons are absorbed and we get 3 omega, 3rd harmonic generation, 4th harmonic generation, etc. And you can see that as we go higher and higher in this, let's say, perturbative scaling, then the probability of observing the higher harmonic photon gets less and less, right? Because we need more and more photons to be absorbed. So as a function of the harmonic order, if we want to see the first harmonic order, where we have a big probability of seeing it, but the second harmonic has a slightly less, third harmonic slightly less, fourth harmonic slightly less probability of seeing it. And this was the common wisdom up to the mid-80s. But then in the mid-80s, Gerard Moreau and Donna Strickland invented chirp pulse amplification, for which they won the Nobel Prize in 2018. And this allowed intensities of on the order of terawatts per centimeter square, which now become comparable, the forces exerted by these fields, to the Coulomb forces that bind electrons in atoms. So Anne Lullier was the pioneer of using this type of laser pulses to shine it on to gas atoms and measure the high harmonic spectrum. So as in the plot I was showing before, in the x-axis we have increasing harmonic order, and in the y-axis we have the probability of observing this harmonic order. And what we see is completely different to what we that we saw before, completely counterintuitive. Of course, we see much more harmonic orders. We see up to 100. This is expected. We have high intensity. But what we see is a plateau in which 2 consecutive harmonics have the same probability of being observed. And then at some particular energy, we have a sharp cutoff, a sharp drop of the harmonic emission. So no one really understood what was going on. So this is the beginning of strong field laser spectroscopy and attosecond science. And the one who figured out what was going on was this guy here, Paul Korkum, who in his seminal paper provided a model for the observations of Anne-Lullier. So in this model, what happens is that the strong electric field, at the peak of the strong electric field, the Coulomb potential that binds the electron in the atom is tilted so that the electron can tunnel out from this Coulomb potential to the continuum. It's in the continuum. Then the laser field drives the free electron in the continuum away from its hole. And at some point, when the laser field changes sign, 1/4 of a cycle later, then the electron can reverse its direction and return back to the hole. And with some probability, it can emit a burst of radiation, and the energy of this burst of radiation is proportional to the kinetic energy that the electron has gained during its laser accelerated trip in the continuum. So these steps happen in a fraction of the optical cycle. So the burst of radiation emitted is a fraction of the optical cycle, which means that if we are using typical titanium sapphire lasers of 800 nanometers with 2 femtosecond optical cycle, what we get is a pulse of radiation that is in the attosecond regime. So this process is repeated every half cycle of the field. So what we get is indeed a train of attosecond pulses, which are separated. Each pulse in the train is separated by half the period of the laser field, the driving laser field. So in the frequency domain, this translates into the odd harmonic spectrum that Anne-Lullier was measuring. So with this model, attosecond science was born because it gave a time perspective to the high harmonic spectrum, and it linked the attosecond motion of electrons to the properties of the emitted light. But it had to take another 8 years to really validate this model, because for this model to work, what we should have is that consecutive harmonics, 2 harmonics which are close to each other, have approximately the same phase. Okay, and this was thanks to Pierre Agostini, who devised the first interferometric experiment which had attosecond stability. And they call this technique RABBIT, reconstruction of attosecond beating by interference of 2 photon transitions. So they basically interfered 2 photon paths, one containing harmonic 2n-1, the other containing harmonic 2n+1, and so they could retrieve the relative phase between the 2n-1 and 2n+1 harmonics in the train. And they indeed found that the phase of these harmonics is approximately the same, and they could reconstruct the attosecond pulse train, which had 250 attosecond pulses separated by half this optical cycle of the driving field, which is 1.35 femtoseconds. So this confirmed the 3-step model of Paul Korkum and initiated attosecond science. And approximately the same time as Pierre Agostini characterized the attosecond pulse train, Ferenc Krausz team was able to isolate a single attosecond pulse. And they did this by noting that at some region of the high harmonic spectrum, there was only one recombination event. So only one path of the electron going out and coming in and recombining. So only one attosecond burst was emitted in this energy region. So they gated this energy region, and they managed to obtain an isolated XUV attosecond pulse. And one of the coolest, I think, and really wanted me to show this slide, things that you can do with attosecond pulses is actually take pictures of longer pulse, right? So we have an attosecond pulse, and we want to take a picture of a femtosecond pulse. So we want to take the picture of the red pulse here. This is really, really short. It's 10 to the minus 15 seconds, but we have a camera which is 10 to the minus 18 seconds. So we delay it, and at several times, so we delayed the two, and we take snapshots of this red field. And what we get is, this is an experiment. This is the light wave of the femtosecond pulse. This is super cool. So this is the evolution of the pulse duration. So from the beginning of the laser until the 1980s, where you have this plateau, because essentially technologically we reached that the pulse duration was one optical cycle. We couldn't get lower than this. But then we invented chirp pulse amplification, in which we access these super high intensities, and we could get pulses which are a fraction of the optical cycle of common lasers. Yes? The attosecond pulse, it's... I mean, well, this is essentially, so you need at least one period of the attosecond pulse, right? So you can go up in energy, and but you essentially need that the attosecond pulse has one optical cycle. So this is the minimum that you should have for a pulse.
Put another way, how high can you go in harmonics? So you can go to 1,000?
Well, the maximum highest harmonic order that they have achieved is 5,000. They went to the kilo electron volts right now with mid-infrared lasers. So, yeah, and the frequency, yeah. So yeah, so this is some current world records. The shortest pulse is 43 attoseconds. This is approximately the time it takes light to travel a quantum dot. So it's super fast. Highest harmonic order is 5,000, and the stronger laser power or intensity is 10 picowatts at the Eli Alps. This is a huge number. So to give you an order of magnitude, this is 10,000 times bigger than the total amount of power, of electrical power in Spain. So it's really huge. But the trick is that it's concentrated in a very short time, so that the energy is not so large. But 10 picowatts is a lot. And focused, we have 10 to the 23 watts per centimeter square, and a field strength of 10 to the 15 volts per meter, which is approaching the Schwinger limit of 10 to the 18 volts per meter, where you can have electron-positron pairs, pair production, and other cool nonlinear effects. So, I want to briefly tell you the application of attosecond science to the motion, to studying electron motion. And so this is an example from my PhD. Maybe you're all familiar with some of you are familiar with the Fano resonance. This is a typical example of electron-electron correlation, in which you have two paths. One is a direct path in which one electron is ionized to the continuum, and another you have a doubly excited state which decays into this other path. So these two paths interfere and give this Fano resonance there. And these Fano resonances have been known and have been measured since the 1960s. But this electronic dance, this electron-electron correlation that leads to this Fano resonance have not been possible, because this electron-electron interaction just happens so fast. Right? So in a collaboration with Allulier, what we managed is to measure the amplitude and phase of this auto-ionizing, this Fano wave packet. So this is the phase that the experiment measured of this Fano wave packet, the phase shift. And with this, we were able to reconstruct the full dynamics of how this Fano resonance is formed, right? So at the first few attoseconds, what we have is a normal resonance, in which we have just like a Gaussian wave packet forming. And then little by little, this doubly excited state, due to auto-ionization, starts to decay in this other, and we start to see the buildup of this interference and the buildup of this dip, this Fano resonance there. So, and just another quick example. This is my last slide before Rui. This is another very cool insight that attosecond physics can give to physics. So, if you imagine like like at the beginning of quantum physics, people were thinking, how long does an electron take to get ionized, for example? So how long does it take an electron to get ionized from the 2s or from the 2p core? Is it the same? Is it different? And these were Gedanken experiments, right? I mean, how could one possibly measure how much it takes an electron to get ionized from an atom? Well, with attosecond science now we can actually. And we measured that the difference of photoionization from a 2s from a 2p orbital is around 20 attoseconds. So we can really measure all of this super cool electron dynamics. So with this, I would like to take over.
Okay. So thanks a lot, Álvaro, for this short introduction to ultrafast physics and attosecond physics. So what I would like to tell you now is what we think, both of us, it is the future of attosecond physics. So actually, attosecond physics, it started with, I would say, with Corkum in '93, but we believe that it still has a lot of future. And one of the promises that we have in attosecond science is to study more complex systems. So in the first 2 decades of attosecond physics, we were devoted to study atoms or small molecules like H2 and 2. But now that we understood how atoms or how small molecules behave or their ultrafast dynamics, now we want to jump to more complex systems. And actually in the last decade, we have 2 main branches. So on one hand, we have like studying complex molecules, and this is not working, and this is the commonest thing. So attosecond science in complex molecules. So we want to study more complex molecules like biological molecules, amino acids, molecules that can have some relevance for biological processes, and in which you can, using these ultra short light pulses, not only see how electrons move in photochemistry, for example, or how electrons in an organic molecule go from one functional site to another functional site, but also we can control these dynamics. So we can selectively say in an ultra-fast time scale, say this electron I want to go to this functional site, and for that I will use tailored light field, okay? And this is being developed also here at the campus of Autónoma, for example, by the group of Fernando Martín at UAM. But here the relevant part is really to study attosecond science in condensed matter, because we are in a material science institute, and this is what we have been doing in the last years. A cluster of people that, as theoreticians, work here at ICMM. Okay, so we have a dream actually. So we want to use these light pulses, these very short light pulses, to try to have petahertz electronics. So I want to give you an idea of what is Moore's law. So it was a law, the kind of empirical law, that stated that the number of transistors that you see here in orange is going to double each 2 years in a chip. And this is following quite nicely, okay? But what is not following quite nicely the Moore's law is the single thread performance. So actually, manufacturers of chips, what they do is just to put more cores onto your CPUs, because they cannot have faster cores. So you see the single thread performance, it has a plateau, but most importantly, the frequency at which your computers work, it's the same as in 2005. So it's like 5 gigahertz. You cannot go faster. With conventional electronics, you cannot go faster. So the dream is to use these kind of intense lasers that are very, very short and try to increase the speed at which we can change the material properties at femtosecond timescales or attosecond timescales. Okay, and this is a picture shown by Ferenc Krausz at this weekend at the Nobel lecture in physics, and I can show you here. So this is a femtosecond laser. So this is a square of the electric field, and then you shine this into a semiconductor, and you measure the amount of carriers that you are injecting into this semiconductor. And you see that this does not go with the envelope of E of t, okay, but it goes with the crest. So in a very few femtoseconds, you can inject carriers into a semiconductor, okay. So these attosecond physics may help us to go from gigahertz to petahertz. That's a dream, of course, okay, but it's dreams that move ourselves forward, okay? And this is a dream by a Nobel winner, so it's not a stupid dream. So it's the dream of Ferenc Krausz, okay? From a theoretician point of view, there is also one thing that is very nice, okay? I'm an atomic physicist by training. Also, Álvaro is atomic physicist by training. And what we think is that attosecond physics can bring a new perspective to condensed matter physics. So if you are a condensed matter physicist, your brain is locked to think about omega and k. That's what you think. So you think about Ashcroft. What do you think about condensed matter physics? What is the first picture that comes to your mind? A band structure. So you have k and omega, which is completely counterintuitive. In our daily life, or in classical mechanics, we use R and T, not omega and k. And this is exactly what we do in attosecond physics. When we work with attosecond physics in atomic and molecular targets, we think about time and space. That's our basic quantities, time and space, not omega and k. What attosecond physics in solids can bring is really the merge between these two fields, condensed matter physics and attosecond physics, okay? So you have people that think on time and space, you have people that think on omega and k, and when you join two completely different things, a new thing is going to emerge. We don't know what it's going to be, but a new thing is going to emerge, okay? And this is attosecond physics in solids. So now you can use these short and intense laser pulses to study phenomena in condensed matter physics that you usually think in omega and k. So your brain really is locked, like you read Ashcroft, you don't see time anytime. And then you can see phenomena that you have learned in Ashcroft, for example, but now think on another perspective, okay? And you can prove electronic dynamics in solids at this attosecond time scale, okay? And also we can ask the question, can we change the properties of solids with this kind of pulses? So we have this engineering of laser pulses. So can we do tailored laser pulses in order to change the properties of solids the way we want? And the answer is yes. So a huge discovery was done in 2011. So this process of high harmonic generation that was discovered in atoms first was discovered in solids in 2011, and this opened the window for attosecond physics in solids, not only in atoms or molecular gases, okay? And not only it was observed in bulk crystals, but also in 2D materials. So you also can see, and you also can do attosecond physics in this plethora of materials that we have in 2D materials, like van der Waals network structures, wherever you want, okay? So what is actually the mechanism that generates harmonics in solids? So once again, it's a three-step model, as Álvaro told you, and it was developed by Vampa in this paper in 2014, and actually it is co-authored by Paul Corkum, and I want just short notice. Paul Corkum is a theoretician, also an experimentalist, but he is the guy that founded attosecond physics. It is completely unfair that this was not a winner of the Nobel. We don't know why, but attosecond physics arises when Paul Corkum gives the explanation of the three-step model. Without the three-step model, attosecond physics would not be anything, okay? So As in atoms, we have a three-step model. So imagine that you have a two-band solid. Okay, so you have a valence band. You are completely electrons are filling the valence band, and the conduction band is completely empty. And at the beginning, you shine a laser field. The frequency of the laser field is much smaller than the band gap. So excitation, as occurs in atoms, is going to be dominated by tunneling ionization. Okay. And as soon as you generate an electron in the conduction band, you generate an electron in the valence band, and then they are going to be driven by the field. So they are going to be driven by the field, by the semi-classical equations of motion that you can learn also in Ashcroft. And since you are not in an atom, you are moving electrons in bands, and bands are non-parabolic, you are going to emit harmonics from this current. So the Bloch current, and that is expressed here, is going to contain non-parabolic terms that will give rise to harmonics of the radiation. Also, as in atoms, you generate an electron and a hole, they will going to propagate, and they can recombine at some point, and when they recombine, they emit a big photon. And this big photon is going to be equal to the difference in energy between the conduction and the valence band, and this will also give rise to harmonic radiation. So this is the simplest picture that we can have for high harmonic generation in solids. But solids are much more than two bands. Okay, you can have strong interactions. Okay, you can take into account the topology of the bands, and we can also try to think about ways to control the electronic degrees of freedom using these light pulses. And at ICMM, as theoreticians, we want to address these kind of questions, okay? And I'm going to show you 3 examples of recent work that we have done addressing exactly these 3 questions. So the first one is electron-electron correlations. So we have studied the Hubbard model. The Hubbard model is like the first model that comes to your mind if you think about electron-electron correlations. And so it's a Mott insulator is really a material that should be a conductor, but it's not because you have electron-electron correlations. So it's an insulator. And it's an insulator because when you have 2 electrons at the same site, they repel each other. They don't like to be close to each other. So these kind of states are disfavored. So then electrons are going to be stuck. They are going to be frozen, more or less. And this material cannot conduct electricity. But if you shine a very, very strong laser, a strong electric field, then you can force one of the electrons to jump and to create these kind of things. And what we have seen is that if we do theoretical calculations and we see how harmonics are generated, so here in the blue line, I'm showing you, so here I start with an insulator, here I end up with a conductor, and you see that the harmonics, if you look at the harmonic radiation, you are really tracking down, tracking in time when you have the phase transition, okay? So the second one is also the topology. As I've told you, the velocity of the electron has to do with the derivative of the band, but you also have another term that is the anomalous current that is proportional to the Berry curvature. And the Berry curvature is the essential ingredient of topology in bands. And what we have seen is that by looking not only to the first harmonic, but to third and higher harmonics, and by looking at the ellipticity of these harmonics, these encode the Chern number of your material. Okay, so you can track down the topology by looking at these ellipticities of high harmonics. Another thing that very cool that we have done is really like these trefoil fields. So imagine that you have a laser that is a circular laser that goes on. That rotates, so it's a circular polarization, and it rotates clockwise. And then you have another field, so you combine this omega field. It's not working, okay. You combine this omega field with the 2 omega field that is rotating counterclockwise. So then if you sum both figures, you have this Lissajous figure of the electric field. Now if you superimpose this electric field, so the Lissajous figure of the electric field, into the lattice, into a real space lattice, like in a 2D material, what you do is that you are addressing the A and B sublattice in a different manner. And now you change this orientation of this triangle. You just change the phase between the omega and 2 omega, and this is just changing the time delay. So you can do this in a femtosecond time scale, okay? So actually, since you are addressing the A and B sublattice in a different manner, what you are doing is really addressing K and K prime differently. So you can use this by changing, and then you change this orientation, and then you can populate selectively K or K prime, okay? And this is a video. A video is always nice to show. Let me see if I can. So now I'm going to show you a video in which the triangle upstairs is going to rotate, and you will see that the population in K prime, the population in K prime is going to alternate, okay? So you see that then you start to populate in K prime, but then the triangle change orientation, and then you end up in K. So you can use this to selectively control what kind of valley you are populating, okay? And this is a little bit of advertisement. So we are doing atto theory at ICMM. So actually, what is the advantage? So actually, we are theoreticians, but what is the advantage that we have with respect to other groups worldwide? The community is very small. It's actually a very small community. But we have a perfect melting pot of people with ultra-fast science background, like me and Álvaro, and also people with expertise in quantum materials, like Pablo and Elsa, for example. And this is really the join and the merging of these two perspectives that I told you before, like the omega K and the TR. So this is really the core of attosecond physics, is to think in both dual spaces, okay? We have expertise in materials, simulation, and numerical computation. We also have two state-of-the-art codes. So one of them is called Iberia. It was developed in 2019, allows for the computation of nonlinear optical response. We can use simple tight binding models that are useful, but sometimes if we want to go hardcore, we can just do DFT calculations and start from DFT band structures, or even more complicated band structures like GW or whatever. It was used in more than 15 publications since 2012. And now we have a new code. It's like our new baby. It's a fully real-time, real-space code. So this really comes because I think more in space and time. So I've developed this real-time, real-space code. We developed this real-time, real-space code, and it allows the inclusion of excitonic effects. Okay, and in development, we are trying to go beyond mean field and to study time-dependent BCS in our cluster of people doing atto theory at ICMM. So we have a huge group of, a huge network. So currently we have experiments, so we do theoreticals, we give theoretical support to a lot of experimental groups at Weizmann Institute in Israel, in Canada, at the group of Paul Korkum, Jens Bigert at ICFO, Matthias Kling at Stanford. We have a big collaboration with theoreticians at MBI, with Misha and Olga Ivanov, at Amsterdam, at Saclay, Lund, at Max Planck, and also at Autonoma. And we are here. Okay, so if we want to, if you want to do something with related to attosecond physics, you can say something to us. We are at the group of theory of quantum materials and solid-state quantum technologies, and we are a group of 6 people. So this is a subgroup within the group, or a cluster of people within the group. This is Pablo, Eduardo, myself, Álvaro, Antonio, and Elsa Prada. And now it's time for ultra-fast questions. Ven, muchacho.
Thank you very much for this fantastic presentation. Do we have any questions? Any comments? If not, let's thank the speakers again. Just a small announcement. announcement. We will have a colloquium dedicated to the Nobel Prize in Medicine and Physiology in January, but we will announce it after.